Next question. Vertical displacement of a plank with a body of mass m on it varying according to law. The minimum value of omega for which the mass just breaks off the plank and the moment it occurs. Just after t equals to 0 are given by y is positive vertically upwards. Fine. So what do we know? Y. Well, yeah, this is like 2 sine of omega t plus, well, what's the sine inverse of 1 by 2? 30 degrees. Pi by 6. Okay. So what can we say? We can say the acceleration, that will be minus 2 omega squared sine of omega t plus pi by 6, and this should be equal to n upon m minus g. So since we want the limiting condition, our n upon m thing is 0, so that essentially gives omega squared. Yeah, do we know what omega is? No. Yeah, I guess it's still fine though. So we just get sine of omega t plus pi by 6. It's gonna be like sine inverses and stuff over there, maybe not. Okay, so it's of mass m and stuff, but that's not really what we want. Oh, so we want the minimum value of omega for which this happens. So that would be, oh, and by the way, this yeah, that essentially means that this condition is when y is maximum. So in that case, this sine stuff, it should just be 1. So we just get omega t plus pi by 6 equal to pi by 2 plus 2 and pi. So yeah, and this just gives omega squared equal to g by 2, which means omega is square root of g by 2. So that part is done. Well, that's not correct. That is also not correct. So out of these two, which one? So just putting this into this thing, right? Well, okay. So this is gonna give us square root of g by 2 and into t plus pi by 6. So since we want the smallest one, it should just be pi by 2 minus pi by 6, which is pi by 3. So t equals to square root of 2 by g into pi by 3. Nice. So pi by 3 into square root of 2 by g. Well, that should be this one, not this one. Next, a ring of diameter 2m oscillates as a compound pendulum about a horizontal axis passing through the point at its rim. Okay, cool. It oscillates such that its center moves in a plane which is perpendicular to the plane of the ring, right? So this is the axis around which is rotating, and here's the point, and this is the center which is moving perpendicular to the plane of paper. So it's perpendicular to the ring as well. Okay, then the equivalent length of the simple pendulum is, fine. So we want equivalent length. So like if we were to find it as 2 pi square root of L by G, well, then what would be the length? Correct. So let's do it. What can we say? The inertia of this thing. First of all, this is just mr squared by 2, because this axis which is passing through paper, well, about that the inertia is going to be mr squared, but using perpendicular axis theorem, this would be mr squared by 2. Now using parallel axis theorem, this will be mr squared by 2 plus mr squared. It's like 3 mr squared by 2. Cool. So that's the inertia. So 3 mr squared by 2 into alpha is the torque. So the torque over here will be, well, if this guy is something like this, so yeah, if this angle is like theta, then this will be mg sine theta over there. Yep, mg sine theta is the one which is gonna act, and it's acting where? It's acting at r, so it should be mg r sine theta. Cool. This cancels, so this is approximately gr theta. It should be negative, but whatever. So alpha is, well, this r cancels as well. It's gonna be negative 2g upon 3r into theta. So we can say K is 2G by 3R. Cool. So our angular frequency, that would be, in fact, for a normal pendulum thing, what do we get? We get alpha equal to, well, yeah, G by L, right? Yeah, G by L theta, which means that these must be somehow like equatable. So this would be the the equivalent length, right? So just gonna get G by L equal to 2G upon 3R. L equals to 3 by 2R. Nice. So it's gonna be 1.5. So it's diameter 2 meter, so radius 1 meter, so it's gonna be 1.5 meters. Next question. A particle of mass m moves in one-dimensional potential energy. Okay, fine. The angular frequency of small oscillation about the minima of the potential energy. First of all, we need to find where this minima is. So yeah, your derivatives should be 0, which means minus 2ax plus 4bx cubed equals to 0. Well, x equals to 0 is one of the things, but that's not correct because, yeah, that doesn't make sense. So x equal to 0, that gives potential energy as 0. Okay, and the other thing which we can do is like cancel these x's, so it's just 2a minus 2a plus 4b gives like minus a plus 2b x squared equal to 0. So x squared equal to a upon 2b. What does this give? Well, that gives minus a squared upon 2b plus bx power 4. So b into a squared upon 4b squared. This cancels, just get 4b. So this should be, well, yeah, minus a squared upon 4b, which is smaller than 0. So that means this is actually the minimum. Okay, so it's gonna be doing SHM about it. Yeah, well, x equal to plus or minus, I guess both will work pretty much the same way. So for our purpose, we will just take this, the positive square root. Okay, and since we want to do SHM about it, let's say x equal to this quantity square root of a upon 2b plus some small quantity h. So this is a small length. Okay, so then our ux just becomes, so I'm gonna ignore all the h square, h cube terms because those will be negligible. So it just becomes minus a into square root of a upon 2b plus square root of, well, actually, no, minus a h. Okay, plus b into x power 4, right? So fourth of this guy. Wait a second. Now we don't want this, we want the force, not the potential energy. Force we already calculated, this is the derivative, and well, actually it should be the negative derivative. So 2ax minus 4bx cubed, that's what we need. So 2ax minus 4bx cubed, I'm gonna put this value of x into it. Okay, let's do it. It should be 2a into all this stuff, which should be square root of 2a square root of a upon b plus, wow, this is tiring. So plus 2ah minus 4b into x cube, right? So cube of this thing will be a square root a upon 2 square root 2 b square root b. Cool. And plus 3 a upon 2b h plus some other stuff which we don't care. So as you can see, these things cancel away. Just have 2h minus, so it's going to be minus 6a, it should be h over there, 6ah, which is minus 4ah. So you just got f equal to minus 4ah. So the acceleration is going to be minus 4a upon m into h. Well, yeah, looks correct. Okay, so that essentially gives us everything that we need about the SHM. So we need the angular frequency of small oscillations about the minimum of the potential energy, right? So this thing is omega squared equals to 4a upon m. So omega is square root of 4a upon m, which is 2 square root of a upon m. A tunnel is dug in the earth across one of its diameter. Okay. Two masses m and 2m are dropped from the ends of the tunnel. The masses collide and stick to each other and perform SHM. The amplitude of SHM will be. Alright. So, yeah, this is like doable. What do we know? Well, first of all, yes, it will do SHM because the gravitational attraction is now proportional to r. Yeah, because mass proportional to r cubed and upon r squared because inverse squared. So that gives linearly related to r. Nice. At first, okay, so we have dropped it from capital R. Say this m is moving with some v. This 2m is also moving with the same v. When they collide, their net momentum will now be mv in this direction, and it has 3m, so now it's gonna be v by 3 over there. Okay, cool. And what do we know? We know that this quantity, so v squared upon 9, this quantity squared, equal to kx squared. Well, k, okay, in fact let's take the ratio. So v squared upon 9 upon v squared, this would be the ratio of the squares of the amplitude, I believe. Yes. So a dash squared upon r squared. It's like maybe I should say r dash squared. So just get r dash equal to 1 by 3 into r. Yes. So that's how far it will go, r by 3. Next question. Two particles undergo SHM along parallel lines with the same time period t and equal amplitudes. Okay, at a particular instant, one particle is at extreme position while the other is at the mean position. They move in the same direction. If I could just draw this thing for me. So at a particular, okay, it's over here, it's moving in the same direction. Okay, so its velocity should be pointing in that way. They are moving in the same direction. So let's just say that this guy is here. Okay, cool. So obviously it's gonna be coming, even if it goes like this or like this. Well, I guess it's gonna go like this. I will make it go like this because that's more handleable. The phase difference remains constant for that thing. So yeah, right now its velocity is like 0, but it will be moving in this direction later on. So what are we given? At particular instant, one particle is at extreme position while other is at its mean position. They move in the same direction. They will cross each other after a further time. So we want them to cross each other. That's weird. So it's gonna go all the way, like, first of all, this angle is 90 degrees. That's what we know. If we want them to cross each other, we want their positions to be same. So this can be happening at this point. When you got this partition as 45 degree, 45 degree. Yeah, at this point the position will be equal, or it can be at this point as well. But I guess this point is not nice. It will have to go back to do this. Well, that's not good. Or it will have to go one full circle and then a little bit. So once again, that's not good. So the immediately next solution would be if it goes over here and this goes over there. Okay, so this angle is 45 degrees, so this complete angle is 135 degrees. So 135 degrees upon 360 degrees into so this is the ratio of the angles into, well, it takes one complete t to go. That's gonna be the time which it needs to go that 130 degrees. So they will cross each other after this time. Well, yeah, it looks correct. So calculate this thing. It should be, well, it's like 45 into what? 45 into, yeah, whatever, let's just do it like this. So 5, first of all, 27 upon 72 t. I guess 9 will work as well. Well, yeah, 3 upon 8 t. That's it. That's the time. Okay. Yeah, looks good enough. Next question. A heavy brass sphere is hung from a light spring and is set in vertical small oscillation with a period capital T. The sphere is now immersed in non-viscous liquid with density 1/10 the density of the sphere. System is now once again set into vertical SHM. Oh wait, vertical SHM. Fine. Oh, so it's a light spring. I thought it was supposed to be a string or something. So it's a spring and it's oscillating. Its time period is t. If the sphere is now immersed in non-viscous liquid with density 1/10 density of the sphere, system is now set in vertical SHM once again. Its period will be okay. So when this was just the spring over there, and you had this mass. Suppose its displacement from the mean position is x, then the force on this would be kx, correct? But now, wait a second, it's t, huh? It's now set in SHM. Its period will be, wait, but you only gave the density. Okay, fine, let's just see what we get. Now it's immersed in the liquid. So if its displacement from equilibrium position is x, what will be the force on it? The force will be, you got kx plus there's an extra layer of liquid which is gonna be pushing it, so it's gonna be rho g, well, times its volumes, right? No, the pressure. Suppose it's a very small sphere. Okay, suppose it's not a big sphere, it's small but very heavy. It's now over here. The pressure is different, sure. What should it just be like? The pressure difference times the area. That's kind of problematic. It's more like the volume times, yeah, but it's just gonna be the one that we got displaced. So this is not making sense. Oh god. I need to think. We know what pressure difference now it has. The volume of this guy. Well, if it's a very small area, we can actually find out what this force should be, right? Well, this is getting complicated. So now we have to find the equilibrium positions and everything. I wish we didn't have to do it, but well, I guess there's no other way. So this guy has mg as its mass. This, suppose is its equilibrium position. At this point, its length is something. Okay, I just got mg. That's the thing. So f is kx. So yeah, that would just be kx, the force on this. Now what's the force on it? Come on, think. Well, we know actually, isn't the buoyant force a constant at this point? Yeah, because it is completely submerged. It's not. Yeah, it's not partially submerged. If it was partially submerged, we would have to take how much of it went further in, so that would add a layer. But at this point, it's not adding any layer because the pressure difference across this body it's constant. So that buoyant force is a constant, which means that no matter where it is, it's a non-viscous liquid. So that factor is also gone, that it's moving and it getting resisted. No, if it's here or if it's here, if it's anywhere, there's no force due to the liquid on this body. Yeah, I mean, by no force, I mean like no variable force. There's going to be a particular force which it has at the equilibrium, and the same force is everywhere else. So that means we still have F equals to kx. Yeah. Well, that's nice. So yeah, it still has the same time period. Now, that's weird, but true. Well, yes, that's correct. Yep. There's no force into the water, so it should be like that. Next. A simple pendulum is oscillating in a lift. If the lift is going down with constant velocity, the time period of the simple pendulum is t1. If the lift is going, okay, it's going down with a wait, what? If its velocity is constant, we don't have to worry about anything. It's, yeah, sure. If the lift is going down with some retardation, well, if it's going down with retardation, that means it is accelerating upwards. So just got this floor which is accelerating upwards. So according to floor, there will be a pseudo force on the thing. What's the thing? Simple pendulum, which means you have bigger G effective now. Okay, it's T2 then. So yeah, T2, for that we have a bigger G, which means T2 is going to be smaller. So T2 is less than T1. Yep, depends. No, it does not do anything like that. A particle starts oscillating simple harmonically from its equilibrium position, then, okay, starts oscillating simple harmonically, yeah. The ratio of its kinetic energy and potential energy of the particle at time t by 12. Wow, that's weird. Okay, so at time t by 12, fine. So the kinetic energy, the potential energy at t by 12, its displacement will be a sine of 1/12 of 2 pi, which will be pi by 6, which is a by 2, I guess. Yeah, yes, so it's just a by 2, huh? So it's potential energy and kinetic energy at that particular. Okay, so its kinetic energy would be half k into a by 2 squared. Yeah, its total energy is just half k a squared, which means its kinetic energy is gonna be half k a squared minus a squared by 4, which is 3 by 4 a squared. So yeah, 3 is the ratio, 3:1. Next question. A mass at the end of the spring executes harmonic motion about an equilibrium position with an amplitude a. Its speed as it passes through the equilibrium position is v. Okay, at the end of fine. Its speed as it passes through the equilibrium position is v if extended to a and then released. The speed of the mass passing through the equilibrium position will be. Really, what kind of question is that? Just use this thing. So half kx, but that would be the kinetic energy which it will have gained. So actually using that, we can just say, well, the spring constant doesn't change really. So v squared is proportional to amplitude squared. Easy as that. So v is proportional to the amplitude. So yeah, it's just gonna be 2v. Well, yeah, that is correct. Next question. A 2 kg block moving with 10 meter per second strikes a spring of constant pi squared. Wait. What? Pi squared Newton per meter attached to 2 kg. Okay. Attached to 2 kg block at rest. Fine. The time for which rear moving block remains in contact with the spring will be. Alright. So this is gonna be really bad. Let's do it. So at this point, it's at its natural length, and what we really care about is the relative velocity, because that will give us the relative positions actually. Fine, so just do it. So this guy is moving like this. Yeah, tensor. Is there going to be any impulsive force? No, there won't be. The spring is always pushing back, sure, but there's no impulsive forces. Or are there? No, the spring is not rigid. It cannot do that. It will get compressed as soon as it hits, and the 2 kg won't be experiencing any force immediately. It will experience when it gets a little more compressed. So yeah, suppose it's at compression x, then this provides F equals to kx. So it's just going to be kx over there. This is gonna be kx over there. This has small m as its mass. Cool. What can we say? The force on this guy will, yes, its acceleration is just kx upon m. This guy's acceleration is also kx upon m, but in negative direction. So for, wait a second, but this x changes, right? Yeah, so it's gonna be kx. Say this body is a, this body is b. This has acceleration kx. So what will be the, yeah, it's gonna be x b, where this x is like the position of b with respect to the origin, minus x a, that should be the length, okay, of the spring. And say it was at an original length L, so it was L naught as its natural length, minus the new length which it has now, xb minus xa. This is the compression. So what can we say about this? What even is L naught? Yeah, we don't know. So you're just gonna get kx, so k times this, more like L naught plus xa minus xb, k times this, that's the force. So this guy's acceleration b is this force upon the mass of b, which is just k upon m into L naught plus xa minus xb. Acceleration on a is minus k by m into L naught plus xa minus xb. But that's not what we want. We want the velocities actually. Sorry, no, not the velocities. We want the positions. Yeah. If we can somehow do that, it will be nice. Or maybe we can just do it like means in contact with the spring will be. Come on, think. Wait a second. So it will most likely leave when it's gonna push, right? It will leave when it cannot provide any further force. Well, yeah, so it will, first of all, it will compress, and then after that, at some point, it will once again come back to its natural length, and then it's gonna leave. Wait, we want the time. Well, the time is really not that easy to find. We will need to do all the stuff correctly. Okay, so now you know what acceleration b is, acceleration of a is. We also got that it's moving at an initial velocity. We need to find x in that case. But actually, since we know what acceleration is, but then it has to do xa and xb, both of them at the same time. Well, that's not good. Oh yeah, we can do this thing. Acceleration of b relative to a. That looks easy. Yeah, just do that. So acceleration of b with respect to a, that will be k by m. It's gonna add them, right? So 2k by n. L naught plus xa minus xb. Well, that's actually more like minus x of b with respect to a. Hey, that's nice. Okay, cool. So now what? Sure, you got this thing and all, but does this really, is this actually an SHM though? We got an L naught. It's linearly proportional, but is it an SHM? If we can say this thing is like h, well, this thing is like d squared by dt of xba, correct? Which, yeah, sure, we can write it as d squared upon dt squared of xba minus L naught. Cool. So if we just let that be h, then we can write it as acceleration equal to 2k upon m into h. So now we can easily find the time period. So for time period, is this gonna be m? Well, yeah, that looks correct. So we just get omega squared, it should be minus over there. Omega squared is, well yeah, it is correct, So omega squared is 2k upon m. Omega is square root of 2k upon m. The time period is 2 pi square root of m upon 2k. Cool. Now what? So 2 pi square root of, the mass is 2 kg. This thing is pi squared, so it just becomes 2. So 2 seconds. So the SHM is 2 seconds, which means, well yeah, it's gonna go forward and at this point, right? So this, whenever it's at the natural length, well, isn't that the equilibrium position? Yeah, that's the equilibrium position. So it will come back at t by 2 time. So it's gonna be 1 second. It takes 1 second for it to compress and then go back once again. Correct. So yeah, 1 second. The amplitude of the vibrating particle due to superposition of two SHMs. Okay. So by superposition, you mean they are just gonna add up, because they, I mean, obviously they cannot be equal to each other at the same time. So yeah, right. Just gonna add them. So we just get sine of. Okay, so we want the amplitude of the vibrating particle. Okay, due to the superposition of these two guys. This is y1, which I can write it as square root 2 times 1 upon square root 2, 1 upon square root 2. No, that's not gonna work. This can be written as 2 sine of sum, which is like omega t plus pi by 6. Cosine of the difference, which is pi by 6, so let's get difference upon 2. So this should be just sine of omega t plus pi by 6. Yeah, y1 is this. Cool. So just 1. Nice. Next question. Two simple harmonic motions. Oh no, sorry, I'm sorry. So cosine of pi by 6 is not 1 by 2. It's going to be 2 into square root of 3 by 2. Cancels. It should be square root 3. Square root 3 is the amplitude. Wow. Two simple harmonic motions, y1 equals to this, y2 equals to this, are superimposed on a particle of mass m. The total mechanical energy of a system is, okay, right, so it's gonna be a sine of omega t plus a cosine of omega t. That's the position. So it's gonna be a well, now it will work, square root 2 sine of omega t plus pi by 4. Okay, cool. The total mechanical energy of the system, well, this is the amplitude now, so it's gonna be half k. Oh, now what's k though? Well, k is still the same. It's still the same. It just, yeah, half k. So it's like gonna be square root of, well, omega squared is k, right? Yeah, omega squared. Half omega squared into amplitude squared is like 2a squared. So it cancels. Just get omega squared a squared. That's the answer. So this would is not. It's actually not correct. It's gonna be m times that. So m omega squared a squared. M omega 6 squared. Next question. While a particle executes linear simple harmonic motion, its linear velocity and acceleration passes through their maximum and minimum values once. Wait, what? So if it's going for SHM, in linear velocity and acceleration passes through their maximum and, okay, in each oscillation, what can we say? Well, it passes through its minimum velocity 2 times. Well, that's for sure. Wait, what even is this? No, that's not correct. Not the peak values. Simultaneously, no. So acceleration passes through there. maximum minimum 4 times in each oscillation. Okay, that's not nice. Whenever you start, well, at this point you got maximum velocity, then over here you got minimum, then over here you got maximum once again, and then yeah, so sorry, over here you got minimum, sorry, maximum over there. So it's just 2 times for sure. It's gonna be 2 times. Yes. Okay, once in each oscillation, no. Next, while a particle executes simple harmonic motion, the rate of change of acceleration is maximum and minimum at the rate of change of acceleration. Okay, fine. We know acceleration is just negative a omega squared sine of omega t plus whatever constant is there, right? So just get dA by dt equal to minus a omega cubed cosine of omega t. So at the mean position, you have that this rate is, well, the mean position, this will be 0, so it's going to be minus omega cubed, well, 0 or pi, that will give minus 1, so it's going to be a omega cubed, and at pi by 2 it is 0. So yeah, at mean positions this rate is maximum, at the extreme positions this rate is minimum. So you want maximum and minimum. Maximum at mean position. A rate of change of acceleration. What? Do they mean the magnitude or what? The rate of change of acceleration. Extreme position, alternatively, extreme position and mean position. Well, it's gonna be either of A or C, depending on what they mean. But since they have given mean position alternatively, it must be that they are talking about what do we call it, the sign conventions as well, right? So the mean position. Next question. A hollow sphere is filled with water. It is hung by a long thread. As the water flows out of the hole at bottom of the sphere, the frequency of oscillation will. So as it flows out, the center of mass will go down, assuming that the water leaves with the same tangential velocity and everything, yeah, so it will essentially still have the same velocity and stuff, just the acceleration will be different. So if your length is gonna increase, it's gonna be t equals to 2 pi square root of L by g, so your time period also increases, right? But what we want, the frequency of oscillation. If time period increases, frequency decreases. Okay, so increasing length, that's gonna decrease our frequency. So first of all, its frequency will decrease, but later on it will increase once again. Once the water level goes down to a particular amount, its COM will start going up because of the mass of the sphere. Okay, so it first decreases, then increases. A cylindrical log of wood floats with length vertical in liquid. It is slightly depressed and released. It executes SHM. Ignoring the viscous effects of the liquid, the period of oscillation depends upon the length and density of the cylinder. Right, let's just find this. So it's already at the equilibrium position. Now if I just put this down a little bit by say x amount, what's the net force acting on this? Yeah, it's just gonna be the force due to this displaced liquid. So it's gonna be this pressure difference, so the new pressure difference, which is like rho gh, so it's change basically, rho gx, because that's how much it changed, times the area. That's the force on this upon the mass. Well, it should be rho water. The mass is like density of solid times the length of the solid, which is a constant, times what? Times the density of the solid, which is, wait, density of solid we already did, times the area, so this cancels. So just get density of water G upon density of solid L times x. So it depends on density of liquid, of the solid, its length and gravitational acceleration. The length of and density of the cylinder, well, it says only upon, so no. The cross-section area and cylinder of the cylinder, and well, it doesn't depend on the cross-section area at all. So B and D are straight away incorrect. The length and density of the cylinder. Well, it depends on them, but not entirely. The length of the immersed portion of cylinder in liquid. Okay. Uh, Immersed portion. Well, how much is that portion? So it's L times the density of solid equals to L immersed times the density of water, which means L immersed is L's. Wait a second, are we getting the same stuff? Oh yeah, we are getting almost the same thing. So density solid. Oh yeah, oh yeah. So it's gonna be G upon L immersed. Huh, that was nice. So yeah, apart from G, it only depends on this Li thing, the length of the immersed part. Weird but true. A simple pendulum oscillates slightly, and by the way, this thing is more or less a constant because it's just slightly depressed, so it won't be making big changes in this. Oscillates slightly above a large horizontal metal plate. Wait, what? Large horizontal metal plate. Fine. The bob is given a charge. Wait, what? Small pendulum. Oh right, so okay, it's some plate like this. There's a spring. There's a given a charge. So now suppose you gave it charge q, the time period. Huh. So it's a metal plate, right? It's a large horizontal metal plate. Okay, cool. So yeah, it will have no effect because guess what? Even though it does shield the inner portion from this charge, right? So why would it even shield the thing? Just wait a second. It's gonna be KQ bars over there. Well, whatever density. Okay, it's not necessarily a uniform density though. That's complicated, and it's more of a large thing. Large thing, which means what? It's not even necessary that it should be a uniform density. So whatever the nature of the charge always decreases. Whether it will be the charge, this increases. Whatever this is complicated. How can you even solve this? Well, if its density was uniform, then there would be no effect. But not necessarily uniform though. There's got to be some way we can solve this. So you want the field inside that to be zero, right? So we field to this Q thing, and if the field is zero inside it, then if I consider any Gaussian surface inside it, well, it will have zero flux for sure. If it has zero flux, because the charge inside it is zero, right? But that's not what we want. This is so complicated. That for sure is not a constant as well. There must be some way. There has to be some way. Who knows? Can it be uniform though? I don't know. Move on. This is a weird question. The total mechanical energy of a particle. I mean, I really want to solve this, but at the same time, it's pretty weird. What can we say about it? Just what? It's not uniform. It's something like that. Moreover, its field varies, right? So they will arrange themselves accordingly, and it won't be uniform anymore. Sure, there will be charges and stuff. those dipoles. Okay, those dipoles won't be having that kind of thing. No, just don't do it. Just don't do it. It's complicated. Next question. And actually, it's a nice question. I guess I will do it later. Total mechanical energy of a particle executing simple harmonic motion is E. When the displacement is half the amplitude, its kinetic energy will be. Hey, haven't we done this like 1,000 times? It's gonna be. Wait, no, potential energy will be E by 4. So it says, okay, displacement is half the amplitude. That means its potential energy is like half kx squared, which is 1/4 of the total energy, which means kinetic energy is 3/4 of the total energy. Cool. So that was like easy. The period of oscillation of a spring pendulum is t if the spring is cut into 4 equal parts. Then, so still the Young's modulus is the same. Okay. The time period corresponding to each part will be. Time period corresponding to each part. So it's dependent on the value of k, right? What do we know for k? It's k gonna change, right? So if you just consider this original spring, pulling it by x produces, say, a strain of something, say E, I don't know, some strain. Okay, now if you got a smaller one, 1/4, yeah, 4 equal parts, so it's gonna be 1/4 length. Pulling it the same thing, same distance, will produce 4 times the strain, which means 4 times the stress as well. That's just 4 times the force. So what we can say is, wait, did I see Young's modulus? It's shear modulus. So it's the modulus of this part, shear modulus, whatever. So what I just mean is that the force constant of this is 4 times the force constant of this guy, right? Nice. So what can we say? Since its force constant is 4 times, its omega squared is 4 times, so omega is 2 times, so time period is half. Okay, a uniform stick of length L is hinged so as to rotate about a horizontal axis perpendicular to the stick. About a horizontal axis perpendicular to the stick, okay, at a distance x from the center. Wait, what? Okay, so it's not like L by 2, it's x. So okay, this is distance x, this is L by 2, this is L, x minus L by 2, something like that. Okay, the value of x for which the time period will be minimum is, first of all, find the inertia of this thing. So about this axis, wait a second, well, yeah, so about this axis the inertia will be ml squared by 12. Yeah, now if we apply parallel axis theorem, it will be ml squared by 12 plus mx squared. So we can say this inertia ml squared by 12 on mx squared times angular acceleration. It should be the torque. So torque is the force, is mg sine theta on the center, which is x away from the axis of rotation. Nice. Yeah, that looks correct, which is approximately mgx theta. So our acceleration, angular acceleration is like, it should be negative over there, but get it doesn't really matter. Mgx upon, well, this m actually cancels, so it's gonna be gx upon L squared by 12 plus mx squared theta. So what do we need to find? We need to find for which the time period will be minimum. So we want the minimum time period. In that case, we want our angular frequency to be maximum, so we want this quantity to be maximum. In other words, we want this denominator to be minimum, right? Time period will be minimum, so frequency is maximum, so this thing is maximum, so this is minimum. What will be the minimum of this thing though? Oh, we can, yeah, well, not this thing actually, there's also x over there. So did I just write mx squared? No, it's supposed to be just x squared, so 1 upon x plus x. Yeah, we can just use gm am inequality. So L squared upon 12 1 by x plus x is bigger than or equal to 2 square root of L squared by 12 into 1 upon x into x, which is 1. So this would be square root of L squared by 3, which is L by x squared by 3. That would be the minimum value, and this happens when these two terms are equal. In other words, x squared is L squared by 12, right? Okay. 2 square root of, okay, did I just miss something? Nah, it's correct. It's pretty correct. This is also L by square root 3, and that is also L by square root. No, L by 2 square root 3. So x would be L by 2 square root 3. That's when this happens. So it's of length 1. So L is 1. Should be 1 by 2 square root 3. Identify the displacement equation, which is simple harmonic. Okay, cool. 5 sine of 2 omega t plus cosine of omega t. Okay, that doesn't look quite correct. This too doesn't look quite correct. This, no, it is definitely not correct. Look over there, the phase is same, even though it's sine and cosine. Well, not technically the phase, but the angular frequency is the same and stuff like that. Okay, so this, sure, this can be written like 5 into 4 by 5 sine and all that stuff, which is going to be sine of 4 omega t plus sine inverse of 4 by 5. Cool. So this is simple harmonic. Next question. A particle executes SHM according to a displacement equation. The velocity of the particle at t equals to 1 by 6 second will be, at t equals to 1 by 6 seconds. So just gave us y. Find velocity. Velocity is gonna be derivative of that. Well, it's in centimeters. That's not good. That's just not good. So 10 centimeters. So it's like 1 by 10 cosine of 2 pi t plus pi by 6 in assignments. T is in seconds. So now it's correct. So now if we take the derivative, it's gonna be, well, 2 pi goes over there, it becomes pi by 5. Why did I put cosine? Well, whatever. Minus pi by 5 sine 2 pi t plus pi by 6. Yeah. At t equals to 1 by 6, you just put over there. So it should be minus pi by 5 sine of pi by 3 plus pi by 6. Is that correct? Looks correct. This is just pi by 2, right? Cancels because it's just 1. So it's gonna be minus pi by 5. Velocity, I think they want it as a vector. So this is gonna be minus 3.14 something upon 5, which is like minus 0.628, something like that. Yeah, meter per second. There we go. y1 equal to this thing, y2 equals this thing. The phase difference between them is, okay, phase difference, fine. So y1 is 3 sine of omega t, y2 though, phase difference, does this look weird for some reason? It's gonna be like 5. This is weird. It's actually more like 4 cosine of, yeah, it's 4 cosine of omega t plus pi by 2 plus 3 sine of omega t, which is 5. Sorry, it's not plus pi by 2 or anything, it's just omega t. Cool. So 5 cosine, actually no, I don't want that. I want sine of omega t plus sine inverse of 3 by 5, Yep. So that's this thing, y2, and y1 is just 3 sine of omega t. Wait, 3 sine of omega t? That's not good. But their amplitudes are different in that case, so I mean, like, okay, their amplitudes are different, not necessarily that their phase difference is not existent. So yeah, it's just the difference of phases. That should be it. So it's just this thing minus omega t. Cool. So sine inverse of 3 by 5, which is tan inverse of 3 by 4. That should be the thing. Next question. A bob of a simple pendulum of mass m oscillates, executes oscillation with total energy E. At initial instant, it is at one of the extreme positions, linear momentum. After a phase change of pi by 6 radians takes place, will be at initial instant it was at one of the extreme positions. After a phase of pi by 6, it's gonna be pi by 2 plus pi by 6, something like that, which is like cosine of pi by 6. Cosine of 30 degrees is square root of 3 by 2, right? So it went from being 1 to square root of 3 by 2, but we want in terms of linear momentum, right? So yeah, it's gonna be something like this. V equals to, I mean, like, momentum is just gonna be mv, so that ratio. Wait, but we are given in terms of energy. Okay, yeah, whatever, we'll just do this. So it's gonna be omega squared cosine of pi by 2 plus omega t, right? So this is v1, v2. Actually, v1 will be when you got cosine of pi by 2, so v1 is just 0. v2 is a omega squared cosine of pi by 2 plus pi by 6, yeah, which is minus sine, I mean, like, fine, minus sine of pi by 6, which is minus 1 by 2 a omega squared. Yep, looks correct. So that's v2. So what do we need to find? So our linear momentum mv, that will be minus 1 by 2 m a omega squared. Our energy E is half k, so it's like half mk x squared. X squared is just a squared in this case. Did I just miss something? This is like v. Its total energy is E. Nah. Okay, so first of all, k is omega squared. A squared. Looks correct. Alright. So we want this in terms of m and E. And omega? No, not omega. But this is gonna be different in that case. That's not nice. Sure, you did find m2. It's just not making sense. You just gave us the total energy, it's not even related to. So just multiply by m first of all. It would be m squared omega squared. Oh, right. That's why it was wrong. So it should just be omega. Sorry. So yeah, and this would be its momentum p. So me is just half m squared omega squared a squared. Square root of 2me is m omega a. And you want half of that. Well, yeah. Is that correct? It now has sine pi by 6. Well, yeah. Yeah, it looks correct. pi by 6 from there, not from there. So its position is not half, but this is half. So yeah, this will be square root of all this stuff upon 2, which is square root of. Nice. Okay, I guess I will stop here. See you later.